Good morning, everybody. Hope you enjoyed the weekend. I'm glad you made the effort to come here. So I'll try to go as smoothly as possible for a Saturday morning.
Smoothly, but it does not mean nothing about the speed.
Yeah. Smoothly that does not mean nothing about the speed, indeed. Okay, so let me start by a recap of what we did yesterday. So yesterday we introduced the peeling with a target. So we're sampling a Boltzmann map according to our favorite Boltzmann measure with a perimeter 2L, that's the perimeter we start with, and a perimeter 2P, that's the target face. And we were peeling those maps. And during those peeling exploration, those filled-in peeling exploration, so at each step you've got an explored map, which was denoted by EI var. Bar means that I'm filling in the holes that do not contain the target face. And so that's the current state of the exploration. I've explored some map here in white, and I have a unique hole with a perimeter, say 2M here in blue. Then my algorithm, my peeling algorithm A, picks for me an edge that I want to explore. And I know that I have three possible outcomes for this peeling step. So either I discover a new room of size 2k, which I denote by an event ck. So this happens with probability qk, the weight of this face. Then the ratio of the disk partition function of the perimeter, which is here m, the half perimeter, which is m plus k minus 1, divided by the former partition function where I had a perimeter 2n here. Or I discover a face which turns out to be the target face, so there is no weight for the target face, and then the ratio of the disk partition function, the one we start with, this WMP, and the one here that we end up with, which is Wm plus k minus 1. Notice the difference with here, there is no marked face anymore because we just discovered it. Or third event, we do not discover a new face, meaning that we are gluing two edges of the boundary of the hole we're going to explore. So we glue this one to this one, say. And in this case, we're separating the holes into two holes. One which will contain the target face, this one, which I denote by a star, which is on the left-hand side in this case, and a hole here of perimeter 2K, say, which is on the right-hand side. And this hole, so conditionally on such an event, this hole is filled in with an independent Boltzmann map with the proper perimeter, with no target, so of low pk. And so this event appears with probability, so wk, that's the weight of the maps you can put here, w m minus k minus 1 p, that's the weight of the outside here, and as usual, wmp is the weight you started with. Okay, that's the peeling transition for the fielding algorithm. Questions? And then we saw that so this provides a Markov chain. Once the peeling algorithm is fixed, we've got a Markov chain for our exploration submaps. And if we focus on the half perimeter of the unique hole of our explored maps, so this is this notation, the partial En star, we saw that this is a Markov chain which is obtained as a simple H transformation of a random walk with state distribution nu. So here is the state distribution nu. So the weight of the positive steps is this qk times ck to the k, and the weight of the negative jumps is this disk partition function, also multiplied by ck to the k, where k is negative here. You have a 2 because there are the two events that may make your perimeter drop. Either you discover a bubble on your left or on your right, hence the 2. And I told you that this is a probability measure. I won't prove it. It's proved many times in the lecture notes, but believe me. And so once you've got this random walk, this step distribution, you can consider random walk on Z with this step distribution and make a H transform of it. So provided that this function is harmonic for the walk, which is indeed the case, and this function has a very simple form again. So H down arrow PL is this fairly simple function. So this ratio this is roughly 1 over square root L, and this is roughly 1 over square root P. Yep, 1 minute. So everything here is for L and P, L larger than 1, and P can be 0. So this formula makes sense when P is equal to 0. The rest, it's always 0, except for the case HP of minus P, which is 1. Thanks. This is what you wanted to say. Okay. Sorry. All right. So we proved yesterday that actually this is a harmonic function for the new walk, and it has a very simple interpretation. So this HP of L is the probability that if you start your new walk from L, the first time you enter the negative half line, so Z minus, that's Z less than or equal to 0, then you do that at minus P. So in particular, when P is equal to 0, that's just the function H down arrow that we saw yesterday in the course. That's the pre-renewal function. Remember, that's the probability that when you enter the negative half line, you do that through 0. Okay? Questions about that? We just saw that yesterday. So then we dive into the realm of fluctuation theory for one-dimensional random walk, and we saw how to condition a one-dimensional random walk to stay positive via H transformations. So just to recap, so then we had a little chapter about 1D random walk. So we had this step distribution nu. The random walk was denoted by Sn. And we saw that when Sn does not drift to minus infinity, then we have this function h of L, which is the same as in this notation as h0 of L. That's just the probability that when you start from L, the first hitting time of the negative half line is through 0. And from this, we form the renewal function h of L, which was just h of 0 plus blah, 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 plus h of L. That was the renewal function. And we saw that this guy is actually harmonic on Z positive or null, if only if the walk is not drifting, it's written there, not drifting to minus infinity. Okay? And then when we had this harmonic function, this positive harmonic function, we could do the H transformation of our walk using this H function, this harmonic function, and we had a process, so Sn upper row, that's the H upper row transform of Sn, which was a process that was staying positive. So it starts from 0, blah, 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 and stays positive. It can come back at 0, but stays positive, non-negative, sorry, and voila. So now let me introduce a slight change. I'll do that this morning. Sorry. So then it's harmonic on Z strictly positive. It's just a shift of 1. And then the process that you get does not start from 0 anymore, because at 0 this function is 0. But it starts from 1, say, and stays above. It can come back to 1, stays above 1, and does not come back to 0. It's just a shift of 1. Right? Why? Because our perimeters will start from something and will never drop to 0. We want to condition it to stay positive and not non-negative. So it's just a shift of -1. Right. So that was yesterday. Questions about that? So since we were into the chapter of fluctuation theory for random walk, let me finish by the third part. And what if? Is that me? what if Sn drifts to minus infinity? So you can think, for example, of a random walk with an expectation and a negative drift. If the random walk has a negative expectation, then it will drift to minus infinity. Then it might not be possible in general to have a version of the walk condition to stay positive. And actually, it is possible if we have the so-called Kramer assumption. And what is a Kramer assumption? It's something really easy once you have understood it. It's the fact that there exists some omega strictly bigger than 1, so that if you sum your state distribution nu k and you tilt it with an exponential factor, you tilt it with omega to the k, so you put more mass on the positive guys and less mass on the negative guys, because omega is bigger than 1. And suppose that this is 1. Okay, so if it is 1, that's an assumption. It's not always the case. But when it holds true, what you can do is you consider nu tilde, the state distribution that you see here. It's just nu of k omega to the k. That's a step distribution, right? Oh, we have time. Ah, good. That's good. Give you a hand.
Thank you, Nicolas.
Thanks. So nu tilde of k, that's a new step distribution, right? And so you can consider the random walk associated, which I will denote by S n tilde. So this guy is very different from S because you can check that this guy actually now has a positive drift. Why? Well, it's something classical. If you consider, I don't know, psi of x, that's the expectation under nu of e to the, let's put a theta here, e to the theta your random variable x. That's the Laplace transform of your distribution nu. You know that this guy is convex, right? It's even the log of this guy which is convex. And so this guy looks like this. At theta is equal to 0, you get 1. And this Kramer assumption tells you that at some theta which is bigger than 0, which is e to the theta is equal to omega, you get 1 again. So let's put a log here. And you know that your function is looking something like that because it's convex. And so what I claim is that if you look at the expectation of let's write it that way, of k nu tilde of k, so the expectation of this guy. So it's easy to see that this is well defined. Why? Because if omega is bigger than 1, you will tilt the negative side by an exponential which is really decreasing. So clearly you have a first moment on your left, right? On your left. And so this guy is well defined. And this guy is what? Is x e to the theta x at theta e to the theta is equal to omega. So that's the derivative of that guy at the point here. And you see that the derivative of your function here will be strictly positive. Here it is negative. Okay? And so what? And so expectation of Sn1, let's say, is strictly positive. And so Sn tilde drifts towards plus infinity. I'm a little loose here because actually those guys could be infinite. I mean, your function is convex, but it could blow up exactly at that point. Paf! It explodes, and it could be that the derivative is actually infinite. But yeah, so strictly positive works for me. Right? So once you have done this change, you are back with a random walk which drifts towards plus infinity. But actually, this guy is a H transformation of my initial walk. Clearly, it's the H transformation for which function? So this guy is a H transform of Sn by H of x omega to the x. Right? So it's a harmonic function which is an exponential function. And checking the harmonicity of this function for the walk Sn boils down to checking this, right? Okay, so what you can do is you do a first H transformation, and then you got a walk that drifts towards plus infinity. So then good. Then I'm back to the setup I had here. I have a walk Sn tilde, which now drifts towards plus infinity. And so I can define for this walk, I can define its renewal function, h up arrow tilde. And I know that this h up arrow tilde will be harmonic on z strictly positive for the walk Sn tilde. And so I can H transform the walk S tilde by the function h up arrow tilde. So what you do, let me summarize here. So what you do in this case, so if Sn drifts towards minus infinity, but you have Kramer, then what you do is you go from Sn to Sn tilde by a H transform, which is, so h of x is omega to the x. You've got this is the so-called associated random walk. And then you go from this one to Sn tilde up arrow by doing a H transform by the function h of x, which is this h tilde up arrow of x. And so clearly you can, okay, if you H transform it and then again H transform, it is an H transform, so you can go from here to there by the H transform, which is the multiplication of these two guys. Yes?
There is something that troubles me is the fact that once you have applied your first H transform, you get something which goes to infinity.
Yes,
And
drifting.
yesterday you explained that, okay, when the basic walk, the new random walk, goes to infinity, we just have plain conditioning to. So why,
Yes.
why in this case?
So this guy is bounded, no problem. It's the same. Obtaining this guy from this guy, you can do two ways. Either you condition your walk to go to infinity, so you condition on a positive probability event, but is that clear that if you condition a walk on a positive probability event, you still have a Markov chain? Not clear. It is the case, but if you do the H transform, you get the same thing, exercise, you get the same thing, and you clearly see here that it is a Markov chain. Good remark. Yep.
If I may note a second question, it's strange that you go. I mean, couldn't you take the H transform for a smaller omega, say the one for which the derivative of log of E, etc. is 0?
Here?
Yes.
Not clear, because then it's not the if you change. If the only exponential function which is harmonic is if you have Kramer condition. It's something that pops. I mean, those who are doing branching random walks, they see that all the time, right? Okay, and okay, if you want a down to earth statement, then this guy is obtained by what you would do to start with, imagining you condition this guy on being positive for time n. And you let n go to infinity. Then you get this guy. But you need Cramer assumption to prove that this works. All right. So we can still condition walk drifting to minus infinity. We can still condition them to stay positive, provided that we have Cramer assumption. All right, questions? So now the goal of today, so I like this lecture, so if I'm not totally killed, I will try to manage. So because now we gather all the tools, and it will be just a piece of cake now to construct those infinite random maps from the knowledge we gathered. Okay? So let's proceed, unless you have questions. No? Okay, so let's see how to construct the Boltzmann map of the half plane. Boltzmann map of the half plane. So as I said yesterday, this guy will be obtained from this picture. So we take this picture there, but we let L, not L, sorry, M, go to plus infinity. So what does that mean? So let's introduce the following transition probability for maps of the half plane. So imagine you've got a map of the half plane, a submap of the half plane. What is a submap of the half plane? Well, it's something like that. You've got some submap, EI, filled in. You've got the root edge here, which is, and on your right, you've got the root face. So that's the root face here. And you've got a unique hole here of infinite perimeter. Okay? Now, same thing as before, you've got an algorithm that looks at this and says, oh, okay, I want to peel this edge. Okay? And now let's see what are the transitions we could get. So first transition we could get is, as usual, we add a face to this thing. We add a face here of degree 2 k. And our new boundary is like that. And that's the former map we explored. All right? So that's still event of type ck. Of course, in those infinite maps, we will never reach the target face, so I'm not speaking about this event. And let's see what the other event is. So what you could do instead is trying to glue two edges on the boundary, say this one and this one. So this happens if you have something like that. Okay, that's your boundary. That's part of the map you explored. That's the map you explored. That's the rest of the boundary. The oriented edge is somewhere like here. That's the edge you want to peel. And so in this setup, you isolated a finite bubble on your left, say of size 2k. And the rest here, it's 2 times infinity. Okay? And so I will call this event, I isolate a bubble on my left, gk infinity. Right? And with my notation, it's just taking those pictures and sending m to infinity. You agree? Right? So far that's something deterministic. And here is the theorem. So theorem. There exists a unique law which I will denote by P infinity, because I took those notation there and I said L to infinity, so it's P parenthesis infinity on the top, on maps of the half plane which are just infinite planar maps with one end, and so that the face on the right of the root edge has an infinite degree, such that for any peeling algorithm, the field-in peeling exploration, so the field-in peeling exploration E0, E1, blah, 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 En inside my map M, so under my probability measure P, is a Markov chain with transitions. So the probability to see an event of type CK, so the probability to see an event of type CK will be this when we send M to infinity. So this will just be, with my notation, this will just be mu of k minus 1. And the probability to see an event of type gk infinity, which is the same as the probability to see an event g infinity k, either swallowing a bubble on the left or swallowing a bubble on the right, has probability nu of, so if I swallow a bubble on my left or right, the boundary size moves by k minus 1, so it's nu of minus k minus 1. And of course, it's half for this one, and half for this one. Okay? Or if you prefer, that's just the limit of this one and this one, which is the same, if I'm not mistaken. And conditionally, of course, and conditionally on an event like that, or like that, the map filling in the finite hole, so the one in yellow, has low pk. It's a Bosman map without target of the proper perimeter. Furthermore, these maps of the half plane, or this distribution P infinity, is obtained as a local limit of maps with large boundary. So furthermore, we have the local. So if you start with a map with a boundary size 2L, no target, or actually you can put a target if you wish. Target or no target. So you start with a very large boundary size. Then this converges locally for the local distance in distribution towards this P infinity. So these are the local limit in distribution of the maps with a large boundary. All right? Is the statement clear? So in a sense, this statement says that I can take this picture and send L to infinity. So if L, the boundary you start with, is going to infinity, then M also will go to infinity. So the boundary size will send to infinity. And you just take limits in all this transition probability, and that works. All right? Yep?
Why is it clear that you will never encounter the target face?
We'll see that. We'll see that. Other questions? Yes?
So here we want the
Let me give you a hint. Okay, the hint is if you start with a boundary of size 2L, where is your target face? How many faces do you have? You may say, well, at least L. Am I going to see the target face near here? Because the target face could be anywhere on these L faces. So if I explore a finite neighborhood, I see 10 faces, it's not in there. Yep? Yes.
So here we need the built-in exploration to so we don't have to keep that.
Sorry, I forgot something. Q admissible, of course. Sorry, back to you, yes?
I was just wondering if there was a need to introduce the other exploration in the first place.
You're criticizing my pedagogical skills or my mathematical skills? I'm not sure.
I was just wondering if the other filling exploration was also going to come in, or if it was just used to introduce the filled-in one.
For you guys, concentrate on the field-in. I will not use the old one anymore. Just the field-in from now on. All right. It's a pity. I want to keep that as well. Okay, let's do that. Can we move the board? Yes. Ah. No, but anyway, I need some room. Okay. Okay, let's vote. This is okay for you? Let's erase this. Yes, I'm here listening to you.
Could you explain the last line, like that notation, P in a circle, mod emphasis again?
This?
Yeah.
Let's take this if you wish. PL.
And what is below the arrow?
This arrow?
Below?
Below? D-loc. Local convergence. That's the local distance that we introduced in lecture 1. All right, so how to prove such a theorem? Well, you first have to be sure that this is a well-defined Markov chain. So to be sure that this is a well-defined Markov chain, you want to make sure that those transitions, they sum to 1. So the transition, sum of the transitions is 1, is equivalent to the fact that nu is a probability measure. Right? Because if you sum this for k bigger than 0, so this is for k bigger than 1, and that's for k bigger than 0. If you sum that, then it's exactly this. Okay, so it's a well-defined Markov chain. So I will always, so I will do, if I have time, I will do that 3 or maybe 4 times in this lecture, and I will always proceed that way. I call this operation checking Tut's equation. Okay, so Tut's equation is checked. Now I want to construct, because so far I tell you that there exists a Uniqlo, blah, 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 blah. So my goal now, that's first operation. Second operation, I will construct a map, a random map of the half plane, which has the law that I wish. Okay? How will I construct it? Well, if this guy exists, I know how to build it by this Markov chain. But this Markov chain works for any peeling algorithm. And so what I will do is I will focus on one peeling algorithm. So let's introduce the peeling algorithm A metric that we saw yesterday in the exercise session. What is the algorithm A metric? So A metric, you imagine that you're given, so let's focus on the case of the half plane, it's easier. Let's imagine that's the part that you have got explored so far. That's your hole here. Your algorithm wants to grow the map, not in a strange way, but in a metric way. So basically, you will discover balls of radius 0, then balls of radius 1, and so on and so forth. So what you will pick is you will pick an edge here on the boundary so that the vertex lying, say, on the right-hand side, that this vertex here is at a distance from the origin here, so that this is minimal. This distance, graph distance, minimal among all edges, let's say A for arête, all edges in the boundary of your map, the external boundary, the one on the hole. Okay, so you look at all the edges that you see on the boundary. So there is one here, there is one here, and so on. You look at all of them, and you pick an edge. They may have several choices, but if there is several choices, you break the tie in a deterministic fashion. For example, by taking this yellow part to be a geodesic which turns as left as possible, for example. Okay? And that's your algorithm. And so what we will do is, let's build a Markov chain, E0, E1, so on, En. That's a Markov chain obtained by the transitions of this board with the algorithm being ametric. What does that mean? And why do I change notation? Because here I'm using big E. I'm just saying, okay, you're telling me what are the transitions, I'm telling you what's the algorithm, so let's build together a map following those rules. And that's very simple to do. It's very simple to do. The thing is, you start from, what do you start from? That's the thing you need to understand. So if you're on a map on the half plane, the initial map is just this. That's a map with one face, one hole, both of infinite perimeters. Okay, so you start from that. And then you apply those transitions with this algorithm. So if you look at this algorithm, then the peeling algorithm says, okay, pick for me an edge with an endpoint minimizing the distance to the root edge, so to the origin. So in this case, you pick this one because you want the right endpoint to minimize. Okay, and you apply a peeling step. So okay, you look at this, you sample your transitions, and so for example, you have something like that. You sample an event E, that's a C2 event. Okay, so let's continue. What's my algorithm ametric telling me now? So pick an edge so that blah, 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 blah. So I will pick this edge. Right? Because its right endpoint minimizes the distance to the origin. Look at the transition. Oh, okay. Here now, what I will face this. I will face a G event. That's a G event. So, okay, that's my transition. Who tells me that? I am facing a G event, so that's, whoops, too bad. So I need to fill this with some map, which is prescribed by my transitions. And I'm facing this new guy. Okay? Now what's the next edge to take? Look at the algorithm ametric. Which one will I take? So this one, right? Because this endpoint on the boundary minimizes the distance to the root edge. And so on and so forth. Okay? So why am I using the notation big E? Because so far, I don't know that these are submaps of something. I'm just building abstract maps, increasing, by this algorithm. So I use the notation big E just to make sure that you guys do not think that these are submaps of something yet. Okay? So let your algorithm run, and I claim that what you want to define, I need a white chalk. What you want to define is just the increasing union. You want to take the increasing union in a sense which is, which I do not precise here, the increasing union of those maps. Okay, so basically you let your algorithm run and see what you get. And you want to define, okay, this will be my map. So I call this step here, I will name it construction by peeling. Construction by peeling with ametric. Okay? Now we need to check. We need to check several things. First thing we need to check is that this guy is indeed a map of the half plane. And that's not trivial. And that comes from the fact that we chose carefully our pinning algorithm. Why? Because imagine if I were not so smart, and if I use a pinning algorithm which is totally silly, which is, for example, you start, so that's your starting point, okay? First edge to peel is this one, say. Okay, you discover a quadrangle. Next edge to peel is this one. Okay, I discover a gulp event like that. Next edge to peel, I'll take this one. Okay, I have a C event. Next one, Château d'Alleuse. Okay? So you clearly see that if I'm applying this algorithm, I am constructing a sequence of growing some maps like that. But if I take the union of those guys, this will not produce a map of the half plane, because I will still have this blue part, which is never filled here, near the root edge. If you look at this stays the same. Okay? So that's step 2, and after step 2, we will always, okay, I need a 4th board. Let's erase here. So what do we need to check? We need to check that with this algorithm, we are indeed producing a map of the half plane. So what could go wrong? Because this algorithm, A metric, is not at all like this one. We want to peel locally to get balls. So what could go wrong? Let me tell you what could go wrong. So I'm not very rigorous here, you will notice, but let me just give you the idea. So the idea is you start building your maps by stuff like that, kind of in a metric fashion. Okay, sometimes you've got bubbles. Okay, up. And you want to grow in a metric fashion. So what could go wrong if En is not a map of the half plane? That means that your root edge is here. That means that some blue part will remain in the limit, like in the example I just erased. In the example I just erased, I was claiming that some blue part near the root edge will remain, that you will see it in the limit. So what does that mean? Okay, so assume I will still see this blue part here. So this edge, I will see it in the limit. This will never disappear, this blue part. So my root edge is here. So if you think of that, that means that, I don't know, this is from a distance 10 from the origin. If this remains in the limit, that means that there exists some point x which remains exposed on the boundary of EI forever. Forever meaning it is never swallowed by the process. It is never swallowed. Swallowed. Okay? And if you think a little bit more, so that's general. But if you use the fact that we're using algorithm A metric, that actually means that there is some point x that remains exposed, okay. And we can furthermore suppose that we're peeling on the left of this point infinitely many often. Why? Because you take one of these points which has minimal distance to the root among those which remain exposed. And by the definition of our algorithm, we will pick an edge on the left of this point infinitely many often. So what does that mean? That means that you have explored some map here. You've got some strange point xi, which will remain here exposed. So you have some blue part here. And we will peel on this edge infinitely many often. So there exists such x so that we peel on the left. So it's an easy exercise. On the left of x infinitely often. So of course I can peel on the left of x and leave x exposed. For example, if I discover a face like that. If I discover a face like that, yes, my x is still exposed. Okay, so now if I peel on this guy, and if I'm identifying this edge with one on the right, like something like this. Okay, I have a gulp here, and that's my new boundary. Then still x is exposed, right? No problem. But you see that what I should prevent is when I'm peeling on the left of x, this one, if I'm doing, I'm not breaking a choke. They're falling into this big hole. So you see that each time I'm peeling on the left of x, if I'm producing a gulp, an event, so let's write it here. If when I have my point x, if I peel on the left of it, and if I have an event g infinity k for some k bigger than 1, then what will I have? I will have this, that's my k, that's my infinity, 2k. And you see that this point, x is now swallowed, it's not exposed anymore. Then x is not exposed anymore. You agree? So that means that each time I'm peeling on the left of x, I should not get this event. But this has positive probability. So come on. If I'm peeling infinitely many often on the left, there will be some time where I'm facing those kind of events. Okay, so you need to make everything clear here, but impossible with probability 1. So almost surely x will be swallowed. I'm a little loose here because x here is random, blah, 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 but I'll let you fill in the details. That's not a big deal. Okay, so this guy that we just construct, so let me erase this. The guy that we just construct by peeling here, up. So we checked, let me put it here, we checked Tutt's equation. Then we construct a map of the half plane, is a map of the half plane. I'm not doing all the details. The fact that it is a map of the half plane is now pretty clear from what you see in the Markov chain, because each time I have a bubble, I filled it with a finite guy, and the fact that the blue guy disappears means that my map will have only one end, and that I will see only one infinite face, and so on. So I'll let you fill in the details. Okay, that's indeed a map of the half plane. So it's a good candidate for this law. Am I done? No, I'm not done, because look at the theorem. The theorem tells you that this map of the half plane, so this M infinity or this law P infinity, should satisfy this. Should satisfy the fact that for any peeling algorithm, this is a Markov chain. What I constructed there is a particular sequence En for a particular peeling algorithm, and I define this as being my guy. So I need to check that this guy satisfies the peeling description. The peeling description here with any peeling algorithm A. Okay? So let's do that. So before we do that, let me make a small calculation. The small calculation is the following. So, calculation. So fix A, a peeling algorithm, and let's look at the Markov chain with transitions as there for the algorithm A. What I claim is that the probability that En is some fixed map B at some step n that's equal to the weight of my map B times CQ, or I forgot to tell, but you remember, CQ, of course, is for ZQ. And ZQ is the fixed point, blah, blah. CQ to the, what I denote by delta star of B minus delta of B. What does that mean? What is B here? So B is some map that I could get after applying some transition like that. So it's a map that looks like this. It's a map like that, with the root edge here, some infinite boundary on the right, and some hole, and one hole on the upper plane, right? What is the boundary of B? Remember this notation for a map M? That's the boundary on the right of the root edge. So this guy is clearly infinite. Remember the notation delta star for a map? That's the perimeter of the distinguished face. This guy is clearly infinite as well. But for a map of this kind, B, we can define, this is infinite, but we can define what is the difference here. Why? So let me, I only slept 4 hours. You can see that. So let me give you an example. Let me give you an example. Okay. That's my map B. Okay, that's my map B. That's the boundary of the hole, and that's the boundary of the root face. What is delta star B minus delta of B? Well, I need to count how many edges do I have more on the hole than on the here. So clearly, all the edges here, which are both part of the boundary and the hole, they do not count. So here, this guy is 1. So this guy, you want to put it 1. And what is the boundary of this guy? 1, 2, 3, 4, 5, 6, 7. So you want to say this is 7. But of course, since we are in the bipartite case, we divide everything by 2. So it's 1/2 minus 7/2. This guy is 1/2 minus 7/2, minus 3. Okay? That just means that I have, in this case, less edges on the infinite hole than I had on the boundary, right? Yes, true. I totally agree. So let's check that. Well, this is easy to check by induction. Unless this is totally false, because there are some maps B that can never appear as some EI. So I need to put indicator that B can be obtained after n steps with algorithm A. You need to be to know that it is possible at least to reach your B. And that's check by induction. You just use those transition probability and everything works well so that you got this. All right, now let me make, this will be the blurriest proof in this lecture, so forgive me. But writing the details of this is a bit nasty. Even in the lecture notes, I'm not happy about how it is written. So if you have comments on that, I'm happy. So what we will do, we want to prove that this guy that we constructed for algorithm A metric satisfies this property. So what we will do is we'll start from this E0. That's my E0. And on the one hand, we can use the algorithm A metric that builds our map En we started with. So after some step, En looks pretty much like a ball, like a filled ball. You've got stuff like that, but it looks like this. That's what you have discovered. That's my En. And now let's do the other way around. The other way around, we will start with this. Not with algorithm A metric, but with an algorithm A that you guys choose. Okay, so we start with some A. So if we start with some A, maybe we have something that does not look like this at all. Like remember the one that I was doing on the board, so maybe you have something like this. Something very non-looking like a ball. Okay? And you do that for 11 steps. 11 being arbitrary. Okay? So N0 steps. So clearly, the one that you will start constructing here has the property for algorithm A, has this property because you build it as this Markov chain with algorithm A. You agree? So clearly, the map that you start constructing here has the property of the right board with algorithm A. And now after these N0 steps, you say, oh, but wait, let's arrêtons les conneries, stop the not the bullshit, but stop the whatever. And now, after this step, let's work with algorithm A metric. Stop algorithm A, now use algorithm A metric. So now you will start trying to correct your mistakes, and you will start discovering something which is like that, you know? And after some step, you will have something that looks pretty much like a ball. Okay? Because after this was a wrong start, then you use algorithm A metric to try to correct this and to look like a ball. What I claim, and that's easy to check, that's a combinatorial fact, I claim that if you use this algorithm A metric, you can look at the stopping time theta of R. That's the first time all the vertices on the boundary of your explored map are at distance, graph distance from the root edge, from the origin, sorry, bigger than R. Roughly speaking, that's the first time you know that you have swallowed the ball of radius R, and you filled in all the holes. What I claim is that if you look on the left, look on the right, and you wait for an R0 large enough, then the guy that you will have at time theta of R0 here, and the guy that you will have at theta of R0 here, they have precisely the same set of achievables maps. Achievables maps are just the maps so that if you explore them, that's the first time that all the vertices on the boundary are at graph distance bigger than, okay? So it's not too difficult to see, but I leave it up to you. So what I claim, again, is you took a wrong start, and then you're trying to say, oh no, let me now discover it metrically instead of this. You can see that on Z2, right? Imagine you're on Z2, and you start discovering a weird shape here, but then you say, no, now I want to discover it metrically. So I will do that. And after I have corrected all my mistakes, I will have the ball. It's the same thing here. So even if the start was not metrically correct, if you apply the metric algorithm, then you will start correcting your mistake until you get balls. Okay, so now I'm claiming that this chain, let's denote it by En prime. You started with A and then A metric. What I'm claiming now is that for this random R0, that this E theta R0, that's the, can you get it? Julien, you get it? There? Ah, yes, I see, okay. Theta prime of E theta prime R0 has the same law as E theta R0. Why? That's my claim. Why? Because I told you that they have the same set of achievables maps. And then I just use this. This tells you that for any algorithm and for any achievable map, I've got this formula. And you see that in this formula does not depend on the history of this process. It just depends on B. Right? So if I have the same set of achievable maps, then they have the same law. Okay? So since they have the same law, they coupled with the same law, and then you can apply algorithm A metric, and this exactly tell you that this second point, it has the same distribution as this guy. Right? Right? Are we good? And by construction, this guy satisfies, the second guy, the En prime, satisfies this assumption for the algorithm A. Since A was totally arbitrary, this works. Well, so I will do that 4 times in these lectures. So of course, meaning that I will do it once, this one, and then I'll say it's the same. Okay? I know it's a dubious point, but focus on it. And I'm glad if you have remarks on how it is written on the notes. In the notes. All right. So now, what we proved so far is, so point 1, point 2 we constructed by peeling. Point 3 we indeed checked that it satisfies this. And there is point 4 now. Point 4 is proving it's a local limit. Proving, so M infinity, which has the law of P infinity, is a local limit. Local limit means this here. And I claim that this is a piece of cake. Really a piece of cake. Why? Now that's piece of cake. And let me tell you why. So fix some maps. So again, there are notational issues there, but let me ignore them. Fix some submap E bar. So some submap like that. And let's compute what is the probability inside my map of the half plane that E is a submap of M. So if I want exactly this submap to appear in M, I know that if I do some peeling exploration, which is exactly the one that I would do to discover this, I should get at some step n, I should get the map E. So this is equal by the formula here, WQ of E times CQ of that's by definition. Almost by definition, sorry. But now let's compute what is the probability that when L is very, very large, that I see E inside my map M. So the notational issue is that this is a map of the half plane. So it must have an infinite boundary. So I will never have, but okay. Just imagine that I cut here, click, click, and I want to see this inside my very large boundary of size L. So what do I need? If I want to see this, there is nothing to do. That's the probability that my map with a very large boundary, L, 2L, looks like I have my map E here, and I need to put something here. Put something here. That's the probability that under PL, my map is looking like that. So if I want a map like that, I know how to get such maps. I start with this piece, and I glue anything there. So that's just, I need to put the weight of the faces here. The weight of the faces here is just W of E bar. And now I need to put a map with the proper perimeter here. So what is the proper perimeter here? It's W of L plus the external boundary here divided by W minus, divided by WL. Why? Because if I started with a boundary of size 2L, and if this is A and if this is B, then here I have 2L plus B minus A. So it's exactly this guy. Right? But now, remember the strong ratio limit theorem? The strong ratio limit theorem that we proved on lecture 2, we proved that regardless of the weight sequence, as soon as it is admissible, the ratio of disk partition function, this was converging towards CQ when L goes to infinity. So if your map E is fixed, you let L go to infinity here, and you get the same thing as here, CQ to the E minus E. Okay, so you know that the probability to see some particular submap is converging towards the probability that you see the same submap in M. And it's easy to see that this implies that the probability that the ball of radius R as defined in the first lecture of R0 is equal to B0, that this converges towards the probability in the infinite half-plane guy that M R0 is some fixed R0. That's easy to see that. It's easy. Okay. And that's by definition convergence in distribution for the local topology. Okay, so it's just a piece of cake now. All right, so we proved that. Questions? You're exhausted? So now let me do the same with map of the plane, not of the half plane. So what I will do now is I will start with the same model here, but instead of letting L go to infinity, I will let P go to infinity. So I will still start from a fixed boundary length for my root face, but I will ask that my map has a target face which is huge somewhere inside. Yes?
Maybe I misunderstood something, but I feel like we proved that for any algorithm stopped and restarted with another, the thing holds.
Yes, but what do I mean by that? I mean that for every fixed k0, 154, then if you run the algorithm for 154 steps with algorithm A, you see those transitions. And I claim that if this holds for every 154, that's the statement. But this is indeed what we proved. But okay, as I said, this is the blurriest proof you'll see in this course. With the equality with the two that are coming. Okay, so let's do that, but now when p go to infinity. Haha. So now let's concentrate and let's do some prep school calculation. What we did basically is here. What we did basically here was to let m go to infinity. Because we took those transitions and we said, if m here go to infinity, then the ratio of those two guys goes to 1. Why? Because it's taking the ratio of those two guys when L is very, very large. So these guys will go to 1, and you have the ratio of this divided by the ratio of this for an L prime. But as you know, this is 1 over square root of L. And here, that's 1 over square root of L prime. But if L prime is L plus K, they are the same. So the ratio here, when m go to plus infinity, go to 1. And that's why we had the new walk here, which is just those transitions here. Now let's see what happens. Let's see what happens if p go to infinity. Okay, so let's see. Let's do a little computation. So if p go to infinity, we've got the ratio of blah, 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 blah over blah, 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 blah. So let's write it down. It's m. Am I going to write it down? Okay, let's see. So let me put L prime is m plus k. And L, okay, no, okay, let me write it. You will help me, right? You will help me. So help me, come on. So m plus k divided by m plus k plus p. 2 to the minus 2m plus k, 2ll, 2 to the minus 2p, right? 2pp, divided by the same ratio with m, so m over m plus p, 2 to the minus 2m, 2, that's m plus k, and that's m, 2 to the minus 2p, 2p, p, right? You agree? So let's send p to infinity. If we send p to infinity, those guys vanish. And we have the ratio this divided by this. This guy is approximately the same thing as this when p goes to infinity. So what do we get on top? We get m plus k times 2 to the minus 2m plus k, 2m plus k, m plus k, divided by the same thing when m plus k is replaced by m. That's 2 to the minus 2m, 2m, m. That's a ratio, right? The ratio of two numbers is the same if I multiply the above and the bottom number by 2. And what is this guy? Da-da-da-da, roulement de tambour, how do you say that? Drums. This is h upper row of m plus q, of m plus k divided by h upper row of m. What is h? Remember, h upper row of L is h down arrow of 0 plus blah, 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 plus h down arrow of L minus 1. And you can check, easy calculation, that this is 2L, 2 to the minus 2L, 2L, L. Exactly this. Haha! So if I let P go to infinity, this ratio of HP transform is this H transform ratio. Okay? I will make a mistake. So now you replace chapter Boltzmann map of the half plane by Boltzmann map of the plane, and we'll write the theorem. Yes? You were not listening in the beginning of that talk.
Sorry.
Can somebody explain to Jean-François? He said, yesterday this was H of L. But at the beginning of that talk, I said, today we will make an L minus 1. Why? Because yesterday I was saying the work was starting from 0 and was conditioned not to hit minus 1, minus 2, blah, 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 blah. But in this talk, it starts from 1, and it's not allowed to hit 0, 1, blah, blah. So it's a shift of 1. And I'm sure you can go through yesterday's lecture by a shift of 1. Another question? Good question, though. All right. So you replace, now you write infinite Boltzmann map of the plane, and there exists a unique law, PL. What will be the notation? Well, we just let P go to infinity, so we want on maps of the plane with boundary size 2L, such that for any algorithm, the fielding, peeling, exploration, blah, 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 under PL infinity is a Markov chain with transitions. What will be the transition of CK? The transition of CK will be this nu of K minus 1, but now it's modified by the H transform of the half perimeter. So the H transform of the half perimeter is just H up arrow of the perimeter after this step. So after this step, it's En plus 1 star. Divided by the perimeter you started with, which is the half perimeter you started with, which is En star. Each time I'm trying to erase this. Thanks. And same for the transition GK1 star, GK star, which is the same as the transition G star K, same probability. That's nu of minus K minus 1, again, modified by the H transform of the perimeters you end up with, divided by the perimeter you started with, the half perimeter you started with. Okay? Or if you prefer, that's just those transitions when P go to infinity. Okay? So you have this, again, on such transitions, when you have a transition GK, the map on transition GK star or G star K, the maps, let me complete the sentence orally, the maps filling in the holes are independent Boltzmann map with perimeter 2K. Exactly the same as here. This does not change. Okay? And last point of the theorem, G star K, last point of the theorem, this law appears as a weak limit. So, second point of the theorem, if you start from a Boltzmann map perimeter L, target phase P, When p go to infinity, you converge towards this law PL infinity. But we have another interesting one. If you start with a perimeter L, no target face, and you condition on having n edges, remember the notation, crochet bracket n? Bracket n is conditioning on having n edges. Yes, the guy with the curly hair, Armand, I think Armand, 10 centimeters so that people there can see. Armand, yes, you, Armand. That's up, 10 centimeters below. Yes, again. Non, oui, oui, Armand, baisse-toi de 10 cm. Non, non, ça c'est se lever, baisser. Baisse-toi, Armand. Baisse-toi, Armand. Baisse-toi. Ah, encore 3 cm. Voilà, merci, Armand. This goes, when n go to infinity, towards this P infinity L. Merci, Armand. Okay, so those guys, which are maps of the plane with a boundary of size L, appears as the limit of finite random Boltzmann maps, and we'll see that. Okay, this theorem is wrong, as written, because, okay, let's try to prove it, and we'll see it's wrong. Okay, so we'll prove it exactly the same way we proved the theorem on the half plane. We first need to check Tutt's equation. Okay, so what is checking Tutt's equation? Checking Tutt's equation is checking that those are transition probabilities. The fact that these are those transition probabilities is exactly equivalent to the fact that H upper row is. So that's the fact that H upper row is harmonic for the new random walk on Z strictly positive. Why should it be? This is equivalent to the fact that nu does not drift to minus infinity by yesterday's. Okay? And this is definition, and we'll see afterwards many equivalent definitions of this, but take this as a definition here. Nu is critical. Okay, so add in the theorem, Q is admissible and critical. So, yep, that works. Tutt's equation is checked. Yes?
So mu is critical or Q is critical?
It's the same. Okay, mu, Q, and the other mu that we had, lecture 2, and sorry, yes, by extension. It's not mu over Q. It's mu or Q are critical. Thanks. So Tutt's equation is checked. If it works, then how do we construct those maps? Exactly as before. Construct a guy that you will call ML infinity by taking the union of this EI, and this EI is the Markov chain you see there with algo ametric. So the difference between what we did a few minutes ago and now is that now you start with a boundary of size 2L, not an infinite guy, you have a boundary of size 2L, and you start your algorithm from this. Okay? So you apply your algorithm ametric, and you see that after some time, the thing that you have discovered, and now I will start drawing my picture in 3D. The thing that you have discovered, this is the boundary you started with, 2L, and you have a unique hole of size whatever it is, and that's roughly the ball of radius r that you have discovered. But of course, when you fill in a hole, it may be that you have tentacles which are going a bit further than the distance, typical distance around the boundary. Okay. So you do your algorithm. You know, you discover a face here, and then a face here, and then you glue and so on, and you see that this guy will grow, and you take the union of those guys, and exactly as before, you check that this is a map of the plane in the sense that this process, blah, 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 the blue thing here will go to infinity, will disappear, and so the local limit is just a guy which still has a boundary of size 2L, but is a map of the plane because it has a unique unique end and only faces of finite degrees. Okay, so you construct the same way, and then you check it satisfies the condition of the theorem with any pinning algorithm. How do you proceed? Same way as before. You consider another Markov chain, En prime, where you first start with algorithm A for some steps, blah, 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 blah. Then you stop and you say, oh, now I will use algorithm A metric. And then you will catch up what you were doing with this algorithm. You couple them, they are the same, blah, 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 it's the same. Equally likely blurring proof. That's the end of the theorem. Ah, no, not the end. The end of this part. So this, I will keep it for tomorrow. And I like, at this point, so this part I will keep it for tomorrow. And at this point, I will be stealing 3 minutes of your time because I will, chapter 3, now you write on top of the page, infinite Boltzmann map of the plane with hyperbolic flavor. Okay, you write that. Is it written? Okay, good. Now you write the theorem. There exists a unique law, PL. Well, P is taken, so you put it H here. HL infinity on maps of the half of the plane. You want it of the plane or half plane? Plane? Okay. Let's do it of the half plane then. Okay, no plane. It's the same for the half plane. Plane with boundary size 2L, such that for any pinning algorithm, the field in exploration under P infinite P under H, like hyperbolic, blah, blah, is a Markov chain with transitions. P, put a tilde here. That's the new tilde. Put the H tilde here. Tilde. H tilde, H tilde. Okay? Proof of the theorem. Check Tut's equation. Tut's equation, to check it, we want that H tilde is harmonic for the new tilde walk. Oh, but the new tilde walk should exist. What is the new tilde walk? The new tilde walk, remember, we need this nu of k, omega k, with an omega bigger than 1 to be equal to 1. And for this was Kramer assumption. For this, we really needed that nu drifts, nu is, the new random walk, Sn drifts towards minus infinity. So with this notation, we really enforce that nu was subcritical. So if it's not critical, it's subcritical. So now assume, okay, it's not critical. So you really assume that the new walk drifts towards minus infinity, that you were not in the critical case. And you assume Kramer. Okay? Then this was all good. Because at the beginning of this lecture, I told you that when the new random walk drifts to minus infinity, if you have Kramer assumption, you exponentially tilt it, and you got this S tilde walk, which was drifting towards plus infinity. And so you can always do that. Okay? So checking Tut's equation with those transitions, the same. Then you construct a guy that I will call H, HL infinity. By doing the same, you apply those transitions with the algorithm A metric. Okay? You check exactly as before that this is a map of the plane, and you check exactly as before that it satisfies this theorem with any pinning algorithm. Same proof. And now you say, but what are those maps? What are those maps? Because the first two ones, we understood. It comes from this discrete model, PLN, where we made L go to infinity in the first case to get the half plane, and where we made P go to infinity to get the plane one. And those guys, the hyperbolic ones, we don't know. Well, actually, Thomas, where are you? Thomas knows for one case, in the triangular case, he knows with Baptiste-Clouf, that's la pub, la petite coupure pub. So those guys that we will see why we call them hyperbolic, Thomas and Baptiste-Clouf, they prove that they arise as local limit of triangulation, in the case of triangulation, of map, not planar map with very high genius, where the genius is proportional to the number of faces. But it's open in the general case. But still, the theorem is that those guys, they exist, and we can still study those guys in the infinite setting, because we just constructed them. So tomorrow, we'll come back. Yep.
Sunday tomorrow.
Ah. Okay. So not tomorrow. So, you know, quand je suis lancé. Tuesday. So Tuesday, we'll recap. So now, I know this was... No, Monday, it's an exercise session. Yes, it's Armand. We shift. It's Armand that will give the exercise session on Monday, and I'm lecturing on Tuesday. So I know this was quick, but this was good for me because, you know, now I have my 3 models of infinite random maps. The one of the half plane requires no assumption of the Q, just admissible. The one on the plane, which requires just criticality, so we'll come back to this, what is the criticality assumption and so on. And the hyperbolic one, which was when it is not critical, and that we can still exponentially tilt it to get a kind of supercritical model, this hyperbolic one. Thanks.